Okay. Hello, Hafide, and aloha. Thank you all for joining us again today. Welcome to the fourth webinar in the Pacific Desk 2022 webinar series. I am David Hitzel, the Pacific Desk Guam instructor. Today's topic of discussion is global sea level rise, observations, models, and complications. The usual reminders before we begin: this is being recorded for educational documentational purposes and is being posted simultaneously on Facebook Live. Please leave questions in the comment section, including your location and affiliation. Questions can also be asked through Facebook Live. A period of oral questioning is allowed at the end of each talk, but please otherwise refrain from having your video or audio switched on. And lastly, the video recording will be saved to view later on Facebook as well as on YouTube. Okay, for our upcoming webinars, the next webinar will pertain to climate change in the US affiliated Pacific Islands. So this is Micronesia, American Samoa. So Hawaii gets a lot of attention with climate change, but there has been some work done for the Micronesian Islands and American Samoa. So we'll have a speaker present on that, discuss some of the local effects specific to small island states in the Western and Southwestern tropical Pacific, tropical cyclone related droughts and their effects on agriculture, infrastructure, and overall quality of life. All right, today's speaker is Matthew Widlansky. He researches climate and sea level variability on seasonal, interannual, and longer timescales. He uses global climate models of the ocean and atmosphere to assess the limits of predicting coastal impacts from sea level extremes. He is currently the University of Hawaii Sea Level Center Associate Director, where he manages research projects relevant to observing, understanding, and forecasting sea level variability and developing products for monitoring and forecasting sea level conditions. As a postdoctoral fellow, he assessed climate model biases for the US affiliated Pacific Islands and performed modeling experiments of climate change processes. Matthew has a PhD in Earth and Atmospheric Sciences from the Georgia Institute of Technology. His dissertation was on the dynamics of the South Pacific Convergence Zone, and his master's thesis concerned the variability of the South Pacific Convergence Zone and its influence on the general atmospheric circulation. He minored in environmental public policy. Okay, so the Intergovernmental Panel on Climate Change, IPCC, predicts global average sea level to rise by up to 1 meter by 2100. This is the conservative estimate, and this is due to melting of ice in polar regions and thermal expansion of water caused by increased global temperatures associated with anthropogenic climate change associated with burning of fossil fuel. So if you mention sea level rise, sort of the lay person, non-scientists, I think their understanding of it is that the Arctic and Antarctic are warming, the ice over land is melting, and this volume of water finds its way to the ocean, increases the volume of the ocean, and thus the ocean rises. And that's apparently 2/3 of the equation. But another third actually comes from what's called thermal expansion. So in level 1 of Pacific Desk training, we discuss thermodynamics, we discuss the ideal gas law. So everybody can understand this phenomena from the ideal gas law. Basically, if you're fluid, the pressure is constant. Then if you increase the temperature, the volume also will increase. So this is basically what happens with the ocean. All the molecules in the ocean, the water molecules, as the water warms, they get a little more space in between each other, and the volume increases. More specific to our talk today, the current global tide gauge data rate of change is 1.8 millimeters per year. However, the rate of increase from, say, the Poseidon, Jason satellites says the global rate is about 3.3 millimeters per year. So this relates to more directly to today's topic in that this discrepancy implies variation in local rates of change versus more large-scale rates of change. And that's what our speaker is going to be talking about. Okay, so in the absence of anthropogenic forcing, there are several factors always at work in modifying sea level height on basin-wide and local spatial scales. The one that everyone's familiar with and overlooked is tides. However, there's also effects of sea level change by Rossby waves, local eddies, seasonal meltwater, various modes of short and long-term climate variability, as well as changes in the atmosphere, including increased wind stress and higher and lower air pressure region. So these contributors have various spatial and temporal scales, but they can be additive, meaning that when they have positive values that coincide with one another, they can become what's called stacked, and this can lead to sea level extremes and/or flood events. So our speaker's work focuses on the global tendency for future sea levels to become not only higher on average, but more variable. This variability will be primarily the result of thermal expansion and the rate to which this occurs. The effects of this variability may even be counterintuitive and lead to lower than normal sea level heights in certain locations. Okay, so for the details on that, then I will turn it over to Dr. Widlansky.
Thank you, David.
I will stop my screen sharing.
Okay, let's see, I'll go ahead and share some slides I put together. David, can you see this PowerPoint slideshow?
Yes.
Okay.
But I can also see everybody else. I don't know if you want it independent.
Oh, let's see. Is that better?
It's still the same where I can see all the attendees on the right-hand side. It's okay though.
Okay. Well, thank you again, David, for that introduction and for the opportunity to share about our work at the University of Hawaii Sea Level Center with this group. I've had the opportunity to attend a few of the Pacific Desk webinars in the past and always learn quite a bit from it. And I think for folks who have attended past seminars, there'll be some similarities in this presentation with a talk that Malta Stuiker gave a couple of years ago about sea level variability. But when I was putting together these slides, what I wanted to do was come about this from the perspective of sharing tools that we use both for the monitoring and the forecasting of sea level variability and long-term changes. This image of this map on the screen, this comes from our sea level forecasting website. Some of you may have seen, and it's last month's monthly anomaly of sea surface heights. This is using satellite measurements of SSH, and the oranges are above normal sea levels, the blues below normal. And you can see for different regions around the Pacific, the variability there. I'll come back to this type of analysis throughout the presentation today. But again, this is going to be a presentation about tools for monitoring and forecasting sea level. So as David introduced, I'm at the University of Hawaii Sea Level Center. We're a center focused on sea level measurement and monitoring. It's tide gauges, and as I'll show in a moment, much more. But our main task is to operate and compile tide gauge data from around the world with a focus on the tropics, especially in the tropical Pacific Ocean. And we do this both by installing and maintaining tide gauges, as well as acquiring data from other centers and maintaining archives. The picture on the left is what one of our tide gauges looks like. This is in Palau in the Western Pacific. And the triangle, maybe the key instrument on there, or radar sensor measuring the water levels. And maybe one of the most important aspects of these tide gauge stations is that they have long-term leveling controls on there. So we're able to use this data to monitor both high frequency variability in the sea levels, like tides, as David was mentioning, seasonal variability, as well as the long-term changes. New in the past couple of years has been our efforts to improve the visualization of the data from these tide gauges. And you can go to our website in a new tool called Station Explorer and see the recent water levels, as well as tidal information in data and products that I could talk a little bit about towards the end of this webinar. And as I mentioned, we also have our seasonal forecasting product on the web. And just like what I was showing for the observations of the past month anomalies, can also use climate model forecasts to see visualizations out the next 1 to 2 seasons forward. And this is mostly what I'm going to talk about today. So as I mentioned, this webinar is focused on products coming out of the Sea Level Center. We have a group, about a half dozen of us, working on these type of products. We're mostly sponsored by NOAA, especially the Global Ocean Monitoring and Observing Program, as well as the MAP program, which is more focused on the research side of things. And our long-term collaborators and partners at NOAA, especially John Mara and Isa Jens, both at the National Center for Environmental Information. And I will point out international collaboration is a key part of this, especially with the Australian Bureau of Meteorology. So I was thinking about what some of the goals may be for this webinar and what I'm trying to do here. Well, first of all, motivate. Why is it important to monitor and forecast sea level? Why is it necessary? But mostly what I want to talk about is the information part of this. A brief recap, what is seasonal sea level variability? And most of the attention towards how we go about monitoring and forecasting. This will be done through some demonstration of the tools that we have for that. And lastly, and I think most importantly, I would like to hear ideas, questions, what we may need to change. As I mentioned, a lot of this is at the research level. So we're always looking for feedback, user feedback, stakeholder feedback of how we can improve on this. And we'll do our best towards that. So I'll put this slide up again at the end, but some questions to keep in mind as I'm talking. Really, what do we need to improve on? So I would like to hear your thoughts just on your overall familiarity with sea level variability, especially on the seasonal time frame. How are you already using tidal information, or maybe not? and the same for climate forecasts. And also ideas of how these tools that I'm going to present could be used by yourself or others. And again, ideas for improvement. Okay, so the motivation side of this, I think for this audience, I imagine you're already well motivated into the importance of situational awareness about the ocean variability, the climate variability. And I think the event earlier this month with the very high southerly swell event that came through the Pacific Islands, coinciding with the king tides, is a good example of this. So the screenshots, this is from the Pongo Pongo NWS Facebook feed, and it provided a very nice chronology and early warning look at the event. You can see they pointed out the likelihood of high surf coinciding with king tides, and the images on the right where there are reports, you can see water over the road, debris over the road, really some significant impacts on the southern exposure of not just American Samoa, but throughout the South Pacific Islands, even as far north as Hawaii. And as I'll mention today, in addition to the high surf and king tides, we also have to consider the long-term sea level rise and the seasonal variability. Did we have high sea level anomalies during this event? Just a little bit of a historical perspective. I got started studying sea level variability, actually looking at the low sea level events. And this image, this is looking out from the University of Guam campus during the last very strong El Nino event. This was a photo taken by Mark Landros. Had this slide in here before hearing the very sad news about his passing, and a person who not only was working on tropical cyclones, but even helped with the sea level science side of things. So very, very sad news to hear about that. But this photo that he had shared with us shows a very low sea level event happening during El Nino. So what do low sea level events do? Well, one thing is they expose the coral reefs that protect the island from wave impacts. So this photo is from American Samoa, some field work that our group did. After that low sea level event in Guam, we knew from past climate variability studies that typically the southern Pacific, the South Pacific has a low sea level event. So we pre-position water level sensors on the reef flats, and we're able to measure sea level conditions during a massive coral reef exposure that happened during that El Nino. You can see this picture when the low sea level event happened, the coral reefs got sometimes referred to a haircut, but it's the die off of the top of the reefs. You can see it outlined in here. So just a little bit of a historical perspective, and it's not just high sea levels that we're considering. It's the full spectrum of the variability. But maybe now with the long-term sea level rise, it's really the high sea level events that are causing the most destructive impacts. And after that El Nino ended, much of the tropical Pacific experienced high sea level events. And in the Marshall Islands, they got hit by these recurrent seasonal high sea level events. I put a circle around October 2016. And that particular month had sea level anomalies in the 15, 20, even 35 centimeters above normal. When I say above normal, the top plot, that's the tide prediction. So that's the same as what you would see classical tide calendar. That's deterministic by the position of the Earth, Moon, and Sun out for the foreseeable future. And the bottom is the difference between that tide prediction and what actually occurred. And I highlight a couple of days on here. And this is an image from that day. And this is a picture of lagoon side flooding on Majura. It happened during high tides, but also above normal sea levels and a wind blowing across the lagoon, piling up water where it wouldn't normally be. Okay, so that was some of the motivation for monitoring, forecasting sea level. But the next few slides, I just want to briefly go over the what. What is seasonal sea level variability? So I want to start with a map of the average sea surface height. The darker reds and pinks, that's higher sea surface height. You can see across the Pacific, there's about a 1 meter gradient in the level of the ocean. And these locations that I've mentioned so far, like our tide gauge in Palau, the photo from Guam of the reef exposed, American Samoa that just experienced a southerly swell, and the Marshall Islands. All of these islands are in an area where typically the ocean is much higher than the global average. And you could ask, why are sea levels higher in the Western Pacific? And the three answers in red below, warm ocean temperatures, converging ocean currents, and a fresher ocean are all components that lead to that typically higher sea level. So then the obvious next question would be, what causes the variability of this? Well, that would be fluctuations in these components. So I like to think of this in a simple schematic sense. So let's consider an island surrounded by a deep, cold ocean with a shallow, warmer layer above. We know that cold water is denser than the warmer water. So the warmer water floats on top. And if that shallow layer is warmer than normal, it expands. So David in the introduction was talking about thermal expansion. That's the process here. Is that ocean layer expands, the relative sea level for the island would be higher. And again, the question, well, what causes that seawater to warm or cool? Same type of features, the climate variability, ocean currents, variability in the solar radiation, or the long-term trend, greenhouse warming, changing radiative balance. Also the winds, currents, evaporation, and even the rainfall can all affect sea level. From the variability of those components, this is the result. This is the observed sea level variability for the Western Pacific using satellite measurements and the tide gauges on all of these islands that are circled here. The deeper orange colors are where there's larger interannual, that's year to year variability of the sea level. So earlier this year, the Pacific Climate Change Monitor report was published. And there's a figure in there, this was produced by Aisha, that I think does a very nice job of summarizing for all the Pacific Islands, the counts of high sea level events. So this is what we refer to as minor coastal flooding. So these are the number of days per year for each of these islands that exceeded an extreme value. Here we use the twice a year return period. A next step for this will be to link these return values to when impacts happen. But we're not quite there yet. For now, these are just counts of high sea level events. And I circled a couple places in years on here just to illustrate the year-to-year variability, where you can go from no high sea level events in one year to 40, 50 days the next year. Just check quickly the time. Okay, so that was sea level variability, but then we also have the long-term trend. So since global coverage of satellite altimetry began in 1993, we can monitor that trend with a high degree of accuracy, precision. And this is a map, again, for the Western Pacific. And the deeper reds are where the trend is larger than other places. Again, same thing, satellite altimetry and the tide gauges are shown on here. And you can see in the Western Pacific, over this full epoch since 1993, much higher sea level rise than the Eastern Pacific. So I mentioned we use satellites and tide gauges to measure these long-term changes. And for most places, there's close agreement between these two measuring approaches to sea level. This is an example from comparing the satellite measurements and the tide gauge around Palau. There are other places, though, where there's a difference between the satellite altimetry and the tide gauge. And one very good example is in the Samoan Islands. Here, this is the NOAA tide gauge from Pongo Pongo. And as many of you are probably aware, there was a large earthquake in 2009. And since then, the land subsidence in the Samoan Islands, well, the tide gauge is attached to the land. So land subsidence affects the tide gauge water level. So we see a difference there between the satellite measurements and the tide gauge. And that difference works out to almost 30 centimeters of extra relative sea level for American Samoa. Okay, so in addition to variability caused by land subsidence, we also have climate variability that manifests in changing sea level trends. These two maps, these are from our the homepage of the UH Sea Level Center, where we show the sea level trend in the first half of the satellite epoch on the left, and then the second half on the right. And you can see for the Western Pacific, the sign of the trend is opposite in some places. So this is an example of interannual to multi-decadal climate variability and how that manifests in changing sea level trends with time. There's a lot of attention in the scientific community about this, trying to understand these sea level trends and provide projections of which places in the globe will have the fastest sea level rise. And unfortunately for the tropical Pacific, there remains a lot of uncertainty. And this is a study from another group in Colorado, where they showed in two different models, the projected trends in sea level rise are opposite in the Western Pacific. That's because there's uncertainty how the winds will respond to greenhouse warming in that region. So uncertainty how the future trend will proceed in the Western Pacific. And I should just clarify, these maps, these are showing the difference in the sea level trend compared to the global mean. So the global mean sea level rise has been removed in these maps. Our work here at University of Hawaii, we're focused on, especially on the sea level variability. And these two maps are using prior generation, the latest generation global climate models to look at how the year-to-year variability is projected to change. And what we find is actually very little uncertainty in that the variability is projected to increase in almost all of the models for the tropical Pacific. And much of this increase in variability we've linked to projections in the effects of the El Nino Southern Oscillation increasing with warming climate. Okay, so we've established today sea level variability, its importance for the Pacific Islands, and that this variability at the very least will be continuing, and according to the latest generation climate models, likely to increase with greenhouse warming. So tools for monitoring this. Well, we have Station Explorer from the UH Sea Level Center. One aspect of that is you can pull up past years and look at the water levels compared to what's average for that time of year, or compared to different years. And we've heard from users, this can be very informative to, for example, compare this year to previous La Nina events or El Nino events. And this time series up here, this is from Palau, but you can do this for any of the tide gauges in our database. Okay, so to shift gears a little bit now into the forecasting side of things. Well, as you're probably well aware, we have tide calendars. They can take all different kinds of forms, from just a calendar up on the wall to a website or whatnot. But a question that comes up is often is my tide calendar saying the high tide is going to be 2 feet or 60 centimeters, but the water level is not that. Why is there a difference? Well, what we're working on are coming up with tools to provide information about the likelihood whether the next month or next season's tides are going to be higher or lower than what the classical tide calendar is predicting. Okay, so this slide, this is a review about seasonal climate forecasting. All forecasts start with observations. We need observations of the atmosphere and the ocean. We need a model. So in our sense, we're using dynamical models. These are of the atmosphere and ocean, land, all coupled together. These are global models. They're initialized from the observations that I just mentioned. They're run in supercomputing frameworks. This is an example, NOAA's computing infrastructure. And then from that, we get many simulations, we get ensembles of forecasts, and we get many different variables. Here for sea level, we're focused on the sea surface height output, but another variable you may be more familiar with, sea surface temperatures, like what are used often for El Nino indices, like the Nino 3.4 index in this image. This is from NOAA's climate forecast system, their latest forecast for Nino 3.4, showing La Nina predicted to continue for about the next 6 months and then ending. The last part about this, though, maybe the most important, is communicating about the output from the climate forecast models. How do we interpret this? What are the applications, like as I'm going to show for sea level forecasting? And what is the uncertainty? So using output from climate forecast models, well, I mentioned before the high sea levels that were recurring for the Marshall Islands after the 2015-2016 El Nino. And what I've done on this image, the black lines are observations either from the tide gauge or from the satellites. And the orange, these are 3-month outlooks from NOAA's climate forecast system for the sea surface height anomalies. And this gives some perspective of the ability to have seasonal outlooks of high or the low sea level events. And again, as you can see, it's by no means a perfect forecast. This is how it looks if you were just looking at the output from the climate forecast model of the monthly anomalies. So these are all, this is in a forecast sense of the 2017 event. The islands there, that's the Marshall Islands. I put a box in a green circle for Majuro. And you can see that this particular model is forecasting anomalies started out near normal, and then by the end of 2017, we're up in the 15 to almost 20 centimeters above normal in the forecast. And that did end up verifying. And this was actually a case study that we used to present to an international audience, trying to motivate the use of global climate models to make sea level forecasts. A lot of information here, but this is just an illustration of how we're taking the initial tide prediction, that faint blue line in the top panel, adding to that the long-term trend in the forecast model anomaly to get the orange line. And this is for all the days in October 2017. And from that total sea level forecast, the verification of what was actually observed is closer. Basically, if we take the tide prediction, combine that with the long-term trend in the model forecast, we get a closer total sea level to what was observed at the tide gauge. Okay, so how do we justify using climate models to forecast sea level? Well, this is, I mentioned the research focus of our group. This is what we work on. A few different papers focused on this. We established the framework for doing just this in 2017 with a focus on the tropical Pacific Islands. More recently, we've tried to look at the state of the art in the global climate models. We looked at it from a global perspective, but it really comes back to the tropical Pacific as being one of the places where there's the most skill in this. So for this particular audience, that's good news. And just briefly to mention what's something our group's working on right now as well, trying to understand why some models perform better or worse than the others. I'll just briefly touch on these points, but I'll focus on the first one. That's the framework for forecasting. It's a relatively simple 3-step process. All the images I'm going to show, these are from our forecast site on the web. We first take the model data, we correct it for known biases or long-term drifts in the model. This is the forecast for this coming September from NOAA's climate forecast system model. You can see forecasting high sea levels in the Western Pacific, below normal sea levels in the East. Step 2, we calculate regional averages. For example, this is from the Southern Cook Islands, and starting from when the model initialized in June, going out 6 months. NOAA's model is in orange. I mentioned the international partnership. The Australian model is in blue. Both of the models for this particular place are forecasting above normal sea levels to continue. And the last of the 3 steps, combining that forecast sea level anomaly with the observed trend, and most importantly, the tide predictions to provide early warning outlooks of potential either high or low tides. In this case, both of the models are predicting above normal sea levels. So at the times of high tide, we would expect even higher extremes than what the classical tide calendar would be showing. Okay, so ongoing work from our group, well, our real-time product, we're limited to only 2 models. So we're researching what other models are available and why some of them perform better or worse than the others. I won't go into this too much detail. It came out in a paper last year. I will mention the aspect about the long-term trend. Most of the models that we work with do not include sea level rise. And even if they do include the sea level rise, there can be long-term drifts internal to each of the models. So we remove that from the models, and what we use is the observed sea level rise in our products. The models do a reasonable, good job of simulating the observed pattern of the variability, the seasonal variability, and that's what we're interested in, because that's what we're looking to forecast for. And these maps, the upper left, that's the observed pattern of variability around the globe. You can see the deep blues and yellows, that's higher variability, like in the Western tropical Pacific. And most of the models do a reasonably good job predicting, simulating that variability. Maybe the most important thing, well, what's the skill, the forecast skill in the models? And we use things like anomaly correlation coefficient or root mean square error to quantify that skill. Just as an example, this is using retrospective forecasts of the past, the multi-model ability to forecast sea level variability. Well, you can see for tropical Pacific, not only are the models skillful according to this metric, but they typically beat persistence. So that means if you have a high sea level anomaly, you could say, well, let's just persist that forward in time, but the models are actually bringing more information to the ability to forecast sea level changes. That's for the tropical Pacific. There are other parts of the globe, certainly, where skill is lower, even non-existent. I'll briefly mention that that skill comes about because the models are simulating the observed features of the sea level variability. This is just images looking at the model output from around Hawaii, resembling what we see in observations. And lastly, what we're working on now, understanding why some models perform better than others. Unfortunately, the NOAA forecast system, it's not one of the better performing models. We see much higher skill coming out of the European Center for Medium Range Weather Forecast, ECMWF forecast, has higher skill, not only in the deep tropics, but extending into the subtropical ocean. So that's an ongoing effort from our group to study the differences here, again, with the collaboration with other forecast centers. So coming up to where I wanted to wrap up with me talking, and I'll just mention again that I've focused on presenting tools or products for the monitoring and the forecasting of sea level variability. And all of this can be accessed from the University of Hawaii Sea Level Center webpage under the forecast area. And with that, I want to put back up the discussion questions. And David, I'll maybe turn it over to you at this point. I don't know if maybe we should do audience questions, or if there aren't too many questions, I can show a demonstration from the web side of things, but it's up to everyone else. So I'm going to go ahead and stop sharing.
Yeah, definitely. At this point in the webinar, I usually open it up to questions, and I let everybody else go first because I always have a couple questions. But yeah, and then this last slide you showed, one of the things I was going to remember to tell you is to show the tools that you have to offer, because those are some of the things that are the most valuable to our program's participants, so that they know where those are. Even if maybe you can put in the chat where some of those crucial websites are.
Okay, will do.
Okay. But other than that, yeah, why don't I open it up to questioning?
Matthew, this is Chip. We used a lot of this out in when I was WCM at Guam, and we did a lot of educating with the sea level out with the Micronesian islands and here on Guam and up in Saipan or the CNMI. And the one thing that we were able to do is show them the differences between the calendar tide and what causes the deviations from that calendar tide, and what to expect during an El Nino, what to expect during a La Nina, and that when the sea level's lower, then the high tide's going to be lower and the low tide's going to be lower, and when the sea level's higher, then the high tides are going to be higher and the low tides are going to be higher. So this is something that we were able to incorporate out there. But with the PIAC, we always use we always take a look at your sea level predictions for each of the island locations, and so it's a really valuable tool, I think, out here. And we're going to I'm doing tsunami work right now with the National Tsunami Hazard Mitigation Program. And we're going to be doing some tsunami source research next year for Pacific sources. And one of the things I wanted to do was to be able to add the sea level component to that, because with rising sea levels, a tsunami that occurs today will be more serious with the sea level rise. So we're going to try to add that component into the tsunami information. Thanks a lot. I really enjoyed your presentation.
Great. Well, thank you, Chip, for that feedback, and just keep us posted any way that we might be able to help with that.
I appreciate that, and I really do depend on the Hawaii Sea Level Center for information. Thanks.
Hi, Matt. Yeah, great talk, and nice to see you again. I mean, we've done this in Kushrai since about 2011 with the timetables that we adjust the timetables every month based on the sea level kind of forecast, originally from the PIAC kind of bulletins, and also PWAMA kind of the Bureau of Meteorology PWAMA model originally, and now every month we use your forecast kind of information and adjust the timetables to shift them up or down depending on that forecast, and that certainly has really helped kind of the acceptability of the timetables kind of there. People we've now got levels related to kind of wharf heights and things like that, so people can actually see much more realistically what those kind of timetables are predicting there. So yeah, I just want to kind of reiterate kind of Chip's kind of point. It's really useful kind of service, and we use it a lot to kind of adjust the Kushrai ones.
Well, good to hear, Doug, and good to see you again. And yeah, thanks. And just it's great to hear when our products are being used, but especially though if you have feedback, things that we can improve, or new ways that we can present this information, we always want to hear it, and can always either reach us from our contact information, my email, anytime. So we're really receptive to that user feedback. Yeah,
thanks. I mean, one of the lessons that we had in Kushrai was we translated it into Kushraian, so the timetables are actually produced in English and also in Kushraian, and that had a fantastic impact. You kind of particularly with the fishermen and things like that. Just having it in the local language was really valuable.
Wow.
Matt, I had one more question. Could you explain the radar? That's a fairly new sensor on the tide gauge, isn't it? And which tide gauges actually have that radar unit on them?
Oh yeah, good question. We're radar is our go-to sensor now. In almost every case, it's our primary sensor. Our tide gauge stations. Typically, we try to have at least one radar, sometimes two, for some redundancy. And then in the water, we have a pressure sensor. And in many places, we still have encoders, which are more of a machine tracking the water level. The radars, what that allows is we can survey the radar point, as opposed to pressure sensors that are in the water, and we have to have other means of calibrating that. There are other approaches, certainly. NOAA uses acoustic sensors primarily on their stations throughout the mainland United States and even in Honolulu. But we've gone towards radars.
Do all the UHC level gauges now have radar on them?
Do all of them? The only places that might not are if we set them up only to measure tsunamis. So there could be some places in French Polynesia where we were asked just to go in and have a tsunami monitoring device, and that would be a pressure sensor. Everywhere else, I think it'd be fair to say we have a radar sensor, and that's almost always our primary sensor.
Thanks, I appreciate it.
One of my comments actually was related to fishermen, like Doug brought up. So I really like the idea of the amended Tide Almanac. And, in a lot of the Western Pacific Islands, Hawaii, your tidal spread during the day is about 2 feet. If you have 6 inches of difference from variability of some sort of climate variability, that seems like a big difference, and it seems like it's something that would be valuable for the general public to know or to understand more about, and have that more widely accessible. Because I think you know, you can hear on the radio, they'll tell you what the tides are for the day, and a lot of the fishermen, they follow that, but that comes straight out of the almanac, and it doesn't include this non-negligible difference. So that's one of the tools that you guys are making that I really like.
Yeah, that's a really good point, David. And well, Hawaii, we have much smaller sea level variability than the Western Pacific. But when we do have sea level anomaly events, one of the user reports we hear coming in are from surfers, and they're saying, hey, we're looking at the tide calendar, but we're seeing a lot of extra water on the reef, or vice versa, it's low tide, the reef's sticking out of the water, what's going on? And that's the sea level variability coming in.
Yeah, the timing on those calendars is good, but it's just the height that the variability that's not.
The one other thing that I was thinking about, and maybe you talked about this and I just missed it, but in variability, you know, there's the issue of frequency and magnitude. So when you talk about increased variability with global warming, with the thermal expansion, how much of that relates to change, you know, frequency in terms of changing more often, and how much of that is just magnitude?
Yeah, good question. I didn't talk about it today. And you could think for tropical Pacific islands, year-to-year variability is almost entirely driven by ENSO, El Nino Southern Oscillation. So in the future, if variability increases, as most of the models are projecting, one of two things could be happening. Either the El Nino, La Nina events are having larger impacts on sea level, or more frequent impacts. And it's different across the models. What we have generally found, though, is it's the impacts of El Nino Southern Oscillation on sea level that's projected to increase. And you could think in a warmer future climate, even if the sea surface temperature variability stays similar, that variability on a warmer mean ocean state is projected by most of the models to have larger impacts on the sea level. So you could think the wind anomalies changing in the future, how those wind anomalies drive sea level.
Okay, so it's very complicated, but it's mostly a magnitude issue. But, okay. Does anybody else have any questions? Otherwise, it's already, what time is it in Hawaii? 4 o'clock.
Thanks for setting this up, Dave.
Yeah, you're welcome. Thank you, Matthew, again for doing this. It's a topic that is important to all our participants. It's a little outside of our normal training criteria, but very, very important. And the tools that you have to offer are very useful for our group.
Yeah, well, thank you again for this opportunity. I really appreciate it, and seeing all of you again, and look forward to hearing from you if you do have any ideas how we can improve things. Thank you.
Sure. Great. Okay, with that, I will close out the meeting, and good to see everybody. I hope to see you guys in person soon. Okay.
Mm.